Okay, class, this is the final three problems of this chapter, number 71, 72, 73. So if you're watching this video, that's what we're going to discuss. If you had issues on this, especially my 10th grade friends, because we did go through number 71 and 72 with my 11th grade friends last class. We didn't get to 73, which this video will definitely cover. Okay, but if you're in 10th grade and you just struggled with these final three problems of the homework assigned, this will be a great review for tomorrow's test. Number 71 reads, a gas sample that has a mass of 0.993 grams occupies 0.570 liters. Given that the temperature is 281 Kelvin and the pressure is 1.44 atmospheres, what is the molar mass of the gas? Okay, so it's looking for molar mass. I'm telling you the biggest difficulty, and it's not even that difficult, is just figuring out which of the handful of equations we use. You know, we've got Boyle's law, P1 V1 equals P2 V2. We've got Charles's law, which relates volume and temperature, V1 over T1 equals V2 over T2. We got Gay-Lussac's law, which is P1 over T1 equals P2 over T2, and then the combined gas law combines them all, P1 V1 over T1 equals P2 V2 over T2. Then we've got the law of combining volumes, which brings in this concept of the molar mass. We understand that the coefficients of a balanced chemical equation tell us mole ratios as well. In this case, liter as well as liter ratios. So it's a new piece of information. And the final equation we know for this chapter is the ideal gas law, PV equals nRT. And because this one involves or is asking for us to solve the molar mass of the gas, the only of those, I guess, 6 or 7 overall equations that actually involve a number of moles variable, it's the ideal gas law. So obviously we're going to use that, but I want you to get into the habit of writing down the given information. Okay, it's very important. You know, we've got given information, we've got an initial volume of 0.57 liters, we've got an initial temperature of 281 Kelvin, and we've got an initial pressure of 1.44 atmospheres. We're also, in this problem, we're told what is the molar mass of the gas. Okay, that's interesting because it's not saying what's the number of moles of gas that this sample contains. It's actually asking for the molar mass, which is a little bit more difficult because it's not a straight up solve for the number of moles problem. It's actually solve for the number of moles first and then use a bit of keyhole knowledge to figure out the actual molar mass of this thing. But as a hint, the only other piece of information that this problem gives us, number 71, is that we're given the mass of the sample of 0.993 grams. So obviously, once we figure out the number of moles of this thing using the ideal gas law, a little intuitive learning, a little keyhole learning, hopefully we're able to get to the answer. So let's do that first. Let's figure out the actual number of moles of this sample using the ideal gas law. So we're going to use PV equals nRT, and because we're given the pressure in 1.44 atmospheres, the pressure is in atmospheres, we can go ahead and use the R value of 0.0821. I told you on test and quizzes, tomorrow's test will involve all problems with the pressure in atmosphere, so you'll use 0.0821, which will be provided for you. You don't have to memorize that, but hopefully by the time you're done with these problems and everything else, you will have it memorized. Anyway, when I plug this in, 1.44 atmospheres for P1 times 0.570 liters for V1 equals N times this special constant, which happens to be 0.0821 when the unit for pressure is atmosphere, and of course times our temperature of 281 Kelvin. Okay, when we do all that math, and I'm not going to go through the math because it's algebra and you're solving for the variable n. When you do it all, as you can see, the math is done here, just in case you're a little not shored up in that. Just look at how it's done. When it's all said and done, we've got a number of moles or an N value of 0.035587 moles. Now, that is the number of moles that this sample contains. Okay, so now I've got both this guy here, okay, the mass of this particular sample, and then the number of moles of this particular sample. So the mass of the sample in red is 0.993 grams. The number of moles of the sample, again, I'm stressing the word sample. The mass of the sample is 0.993 grams. The number of moles of the sample is 0.035587 moles. And I know that essentially molar mass is a function of the grams divided by the moles. So I'm giving the mass in grams of the sample, again, here, and then the number of moles of the sample. So if I simply, you guessed it, divide the mass of the sample by the number of moles of the sample, I'm going to come away with my molar mass of this particular gas. So it's not as difficult as it looks, but when I do divide 0.993 grams by 0.035587 moles, notice I have grams per mole. That's what we're looking for, folks. And when I divide that out, I get 27.9 grams, which is, in fact, the correct answer. Okay. So if you had a question on that one, I invite you to go back and re-listen, okay? Rewind the YouTube video a little bit. But let's go on to number 72. How many moles of helium gas would it take to fill a balloon with a volume of 1,000 centimeters cubed when the temperature is 32 degrees Celsius and the atmospheric pressure is 752 millimeters of mercury? Okay, so again, we're being asked for number of moles in this problem, okay? The only equation that involves number of moles we know is PV equals nRT, or the ideal gas law. So we're going to use that thing again. That being said, the most difficult part of this problem is that every single one of our units is unworkable to us. Okay, so I've got a unit of volume in centimeters cubed, which I'm not comfortable with. I've got a unit of temperature of degrees Celsius, which I don't need. I need Kelvin. And I've got a unit of pressure at 752 millimeters mercury. When I don't want that, because I want my pressure in atmospheres, because on my test, I know that the ideal gas law involves an ideal gas constant, which is dependent on the unit of pressure I use. And I like the unit of pressure atmospheres, and I use 0.0821. So I've got to convert all three of these things. So again, get into the habit of writing the given information down. First thing I have to convert here, as you can see, is the volume. I told you way back in the day that a cubic centimeter represented here. Okay, this cubic centimeter is just another, it's synonymous, it's another way of saying milliliter. They mean the same thing. Okay, so I have 1,000 cubic centimeters, therefore I have 1,000 millimeters. And a quick conversion of converting 1,000 milliliters, we know that 1 liter is essentially 1,000 milliliters. So quick conversion, either in your head or on paper, we realize that 1,000 milliliters is in fact 1 liter. So we've made our first conversion. We've got the unit in liters, which is what we need. Temperature, it's a little bit easier. We're going to take our 32 degrees Celsius and just simply convert it into Kelvin by adding 273, the value 273 to it. And 273 plus 32 is going to get us 305 Kelvin. I will not be providing that for the test. You have to know how to convert from degrees Celsius to Kelvin. And then finally, pressure. This would be provided for you on the test, at least the conversion factor here of 1 atmosphere. By the way, this is your conversion factor here. 1 atmosphere, okay, is going to equal 760 millimeters of mercury. So simple conversion here, we come away with 0.987 0.98947 atmospheres, okay? And again, the problem is straight up asking for number of moles when we're given the volume, the temperature, and the pressure. Therefore, we just simply use the ideal gas law, PV equals nRT, 0.98947 atmosphere times the 1 liter equals N times the ideal gas constant of 0.0821 times 305 Kelvin. Again, I have the algebra stipulated here, okay? 0.98947 times 1 is 0.98947, because any number times itself is 1, or excuse me, is itself. Any number times 1 is itself, the identity property of mathematics. Okay, and the other side, 0.0821 times 305 is going to get us 25.405. And then I simply divide both sides by 25.0405 to get n by itself. And when I do so, I come away with an n value of 0.093, or excuse me, 0.0395. I can't read what's on the screen. 0.0395 moles of helium. So that is the number of moles contained of helium contained at those particular temperature, pressure, and volume. Okay? Again, if you have questions, just quickly rewind and listen to it again, and hopefully you should be good. Let's go on to number 73. Okay? Number 73 reads, a gas sample is collected at 16 degrees Celsius and 0.982 atmospheres. Okay? So we have a sample of gas being collected. There are always going to be gas in this chapter. Okay? If the sample has a mass, oh, here we go again, a mass of the sample. So I have a 7.4 gram, 0 gram mass of the sample. All right, I'm probably going to have to go back to number 71 to review a little bit to figure out how to figure out the molar mass of something. But here we go. All right, given that mass of the sample again, and a volume of 3.96 liters. Okay, pretty straightforward so far. Find the volume of the gas at STP and the molar mass. Oh, two-step answers, right? Two answers to this problem. So we knew molar mass was coming because they gave us the mass of the sample again like they did in number 71. And hopefully we've learned 71 enough just to be able to solve at least the first part of the answer to number 73, which is the molar mass. But what about this volume of the gas at STP thing? Well, let's talk about that a little bit. So again, I want you to get into the habit of writing down what the given information is and then telling me what's missing and then maybe some other pieces of information. Okay, that being said, I have a temperature, T1 of 16 degrees Celsius. Okay, that's no good to me. I need to convert that into Kelvin. I do that by adding 273 to 16 to get 289. I'm given a pressure in the units that I like, which is atmosphere, so that can stay as is, 0.982 atmospheres. And then a volume in the unit that I like, 3.96 liters. That has to be our initial volume because ultimately the problem is asking for find the volume of the gas at STP, which we know to be, as I wrote down here, 0 degrees Celsius and 1 atmosphere. So in blue, I have my given information. In red, I have some seemingly superfluous information, okay, which is sometimes the problem's tricky and it'll just throw useless information your way. Not in this case. You're going to need to know the mass of the sample, this piece of the puzzle here, in order to solve for the molar mass, because that's what the problem is asking for in its first, as one of its answers. And then you're going to need to know the fact that STP, and you need to know this will not be provided, you have to know it. Big STP, standard temperature and pressure, is by definition to 0 degrees Celsius and 1 atmosphere. Now, if I'm starting with 16 degrees Celsius up here and a volume of 3.96, and I'm going to 1 atmosphere and 0 degrees Celsius, obviously I'm moving things along. Okay, so I'm going to need this information. Nothing superfluous in this problem. What I'm going to need in order to solve for the first part of this, the mass of the sample, in order to solve this, I need to figure, like we did in 71, I need to figure out the number of moles. So, of course, any gas law that asks for you to find the number of moles, you're going to have to use our ideal gas law, P equals nRT. Plugging everything in, I'm not going to go through this, you can see it coming up. Plugging everything in and solving for n like we've done the other two problems on this video, I come away with an n value of 0.163895. That's the number of moles. And like we did in number 71, we've got to remember that grams per mole. Okay, that's what we're given. So I'm giving here, again, going back to what I'm given a mass of the sample, and that's key, of 7.40 grams. And I'm given the number of moles contained in that sample of 0.163895. And I'm given a general formula of grams per mole. So I simply divide the mass of the sample, 7.4 grams, by the number of moles of that sample of 0.163895 grams. And when I do so, I come away with grams per mole, in this case 45.15 grams per mole. So that's our answer, ladies and gentlemen, to the molar mass in number 73. Moving on, this is where I need now I'm given a set. Okay, I'm given an initial temperature, folks, of 289 degrees, or excuse me, 289 Kelvin. I'm given an initial pressure, 0.982 atmospheres. I'm given an initial volume of 3.96 liters. I'm asked to figure out what the final volume will be at STP, but my secondary or final temperature, 0 degrees Celsius, which is 273 Kelvin, and my final pressure is going to be 1 atmosphere, because 0 degrees Celsius in 1 atmosphere is, by definition, standard temperature and pressure. Okay, so I'm going to use P1 V1 over T1 equals P2 V2 over T2. And as I said, the most difficult part of these problems, ladies and gentlemen, is just figuring out what formula to use. But because I'm done with dealing with the moles of this problem, and I'm just given an initial set of P, T, and V, and I'm looking for the final volume when I know the final P and T because it's STP, I can just go ahead and plug in what I know. Okay, 0.982 atmospheres, the initial pressure, times 3.96 liters, the initial volume, divided by 289 Kelvin, the initial temperature of 16 degrees converted into Kelvin, equals the final pressure at STP is, by definition, 1 atmosphere times V2, because I'm trying to solve for my volume at STP, divided by 273 Kelvin, because 273 Kelvin is equivalent to 0 degrees Celsius. Again, I don't show the math in this one, but if you have issues with the math, you need to take out an algebra or something and hem up before this test. I doubt any of you really do, but it may be a good idea if you do. So doing all that math, I come away with a volume, V2, final volume at STP is going to be 3.67 liters. That's it, folks. That's number 71 to 73. So if you have questions on that, this is the video to watch, or you already have, so that's pointless. Peace.